Alright, so in this video, we are going to tell you how to design a NAND gate, NOR gate using CMOS transistors, and we are going to do simulations in LT Spice as well. Okay, if we look at a NAND gate, the logic for the NAND gate, we know it has two inputs and one output, and we try all the combinations for the input. It's going to be 0, 0, 0, 1, 1, 0, 1, 1. And because this guy equals to this, which is a NAND gate, so we just plug in A and B into here. We're going to get a 0 and 0 not will be 1, 0 and 1 not will be 1, 1, 0. Okay? So we are looking at the truth table, and we want to get a circuit to implement all the logic here in the truth table to make it work. All right. So before we do anything, we know there are two inputs. So we need two, at least a pair of NMOS to implement something. So now let's take a look at 0. First, when the output is 0, we need both A and B to be 1. Okay, so we can use two NMOS stack on the top of each other, and we ground the source of the bottom one, and we get a Y here. So if you look at this one, we have to turn on both A and B, give them a 1 here, which is logic 1, which is 5 volts in the simulation. And only this when this happens, so you have, for example, you have two faucets in the pipe in the pipe, and you have to turn on both of them to make the water flow through to the ground. So the same concept, you have to turn on both of the transistors since they are in the same channel, in the same wire, to make sure this one can be shorted to ground. Okay, this is how you can make the ground happen for here. So what about ones? So if you want to make the output to be 1, you need a VDD, which is actually the voltage source. We just call it VDD right now. Okay, you want to make something to be connected to the ground, to the VDD, when any of them are being turned on, or both of them are being turned on if they are PMOS. So if you draw PMOS in parallel, let's take a look. So for example, here's the output, right? And we connect the two source terminal of the PMOS to VDD at the same time. And here's A, here's B. So if we, for example, when we can get a Y to be able to equals to logic 1 here, which is VDD, right? So if we get 0 and 0, VSG here. If you have a 0 as for A, then VSG is pretty big. It's VDD minus A minus 0 will be VDD, which is pretty large. Well, definitely larger than than the threshold voltage for the PMOS. The same concept. So the conclusion here is you can turn on, which is you give a 0 to A, so you can connect this one to logic 1, or you can only turn on this channel. You can also connect the Y to logic 1, or just turn on both. So which is exactly what the inputs here, 3 cases, and for all of them, you can get a 1, logic 1 for the output. So if you combine these two parts together, you can implement the full logic in the truth table. So which means a NAND gate will look like this. If we connect this one to VDD, which is logic 1, right? And then two NMOS in series, And since we have AA, BB, so actually you can theoretically you can short them together. So A is controlling these two terminals, and this one is going to control these two terminals. Yeah. So sometimes the video is just frozen over there. I think the laptop is trying to back up the video we just recorded in the process. So if there's something happens, they can still recover that easily. But this laptop is a pretty good one. But I can see this kind of frozen a few times. If the video is pretty long. But actually, my previous laptop won't have that issue at all. But that one was the power cord was broken and they couldn't use it anymore. But it's just a little bit disappointing. Like this one, also have a Intel 7th generation CPU or something at 16 gigabytes for the memory, but still have this kind of issue. Right. Apologize for this kind of a frozen. Every time you see that, they're just stuck there. Right. So let's come back to this schematic. So now we have the entire circuit over here. So this part will be A, B naught, because that's exactly the NAND logic we designed for. So the circuit is going to serve for this truth table. So that's a NAND gate. So what about NOR gate? The NOR gate. So the first thing come first is we still need to look at the truth table, and the possible combinations are 0, 0, 0, 1, 1, 0, 1, 1, right? So we just plug in all these logic numbers into this operation and we can find out the result. So 0 or 0 not will be 1, 0 or 1 not will be 0, 0, 0, right? Because whenever you got a 1 in the OR operation, if you are the coach for the basketball team, then you can pick up the best player. You don't have to have this guy on the court, right? You win the game. So you got 1 here for this part. And you have a bar on the top, so it's going to inverse the result, whatever you are going to get from this OR operation. So it's going to be 0, all zeros here. So let's use the same strategy to find out the circuit. And so let's look at this part first. Okay, if you want to get to 0, so usually we use NMOS for the conduction to the 0, and you can find out, since we know for the NMOS you need a logic high to turn it on, so you can have one of them to be turned on, one of them to be turned on, or both of them to be turned on. So which means you need these two NMOS in parallel. Because only in that case you can make this output to be connected to 0 through the channel of the NMOS by either turn on A or B or both of them, right? So that's the bottom part. So on the top, you have to turn on both the two PMOS at the same time. So that looks like this. Right? And now we just put them together. Right. Yep. And we just short all the A's, which are the same terminals, and all the B's, which are the same terminals. So that's a NOR gate. Right. So you must be wondering, how can I get a AND gate and OR gate from this stuff? Actually, it's pretty simple, and you just add an inverter at the end of the circuit. But usually we don't do that in the real circuit design. We have all these gates available. If you want to invert it, you invert it outside, which means you do not really, in the physical device they are, because the symbol is not actually exist in a real IC chip, but the transistors does. So, but usually in the schematic design, we do not directly draw an inverter here. Now let me show you how you can do that, so you understand why what I'm saying. Actually, it's something like you want to know before you go to the simulation. Okay. So for example, the AND gate. So definitely, and you know that AND gate is, when you have a NAND gate, you just invert that, and you get an AND gate, right? So definitely you can do that. You can. So you have PMOS, two PMOS on the top, which is a NAND gate, and NMOS, and like that, and have two inverters here. And here's the output for the NAND gate, and you invert it, you get the AND gate. VDD just share on the same VDD and share on the same ground. So here is going to be the AND gate. Okay. So I think we didn't really cover the inverter just now, but let's get into it right now. So the inverter, why this works purposely for the inverter. So if you have a PMOS on the top and NMOS at the bottom, and you short the two gates, and you have A here, and you have VDD here, and you have a ground here, so the output will be A bar. So that's the inverter, right? So that's a symbol for the inverter. Why is this the inverter? Look at that. So when you, for example, you have a curve, you have a voltage plot. It's frozen again. So a voltage plot, and here's A bar. Okay. So in the beginning, your A is logic high, and when A is logic high, you turn on here. So this one is being connected to the ground. So in the beginning, A bar is actually 0, right? But actually on the axis, you have your input starting from 0. So when the input is 0, this one is disconnected and this one is on. So A bar is being connected to VDD. So which means you have a voltage logic high here. So when you start increase your voltage at A, which means it's going to the right side of the axis because A is bigger on that side, on that direction. So, when A is bigger and bigger, the NMOS is being turned on more and more, but PMOS is going to be shut down because your VSG is getting smaller and smaller. So that's why finally you have a curve like that. So at some point, your output goes to 0, but your input is pretty high. So that's why it's inverting the result, because when input is 0, you get a voltage high. When the input is pretty high, you get your result to be 0. Okay, so that's why this is an inverter, and vice versa. If you go backwards, it's going to follow this curve again, right? So it's going to follow that. So which means so the output is always inversed to the input, right? So here, that's why we can use a inverter here to make up an AND gate. So it's the same concept. For the NOR gate, you use for the OR gate, you use a NOR gate at the very beginning, and then add an inverter after that. So VDD actually they are shorted in the real circuit, same thing as ground. And Y here equals to A or B. That's an OR gate. Okay. Now let's go to LD Spice. Let's try to make up these gates in LD Spice and do the simulation. Right, this is going to be a pretty long video, so I think probably I will pause here. And in the next video, I'm going to show you how to simulate this, how to make up these circuits in LD Spice and make a symbol to wrap them up and do the simulation. All right, we'll see you in the next video.